Greetings. Welcome to today's class. So today we will look at a very important concept called as relative stability. Before we move on to relative stability, I just want to briefly mention about Nyquist plot, right? So because we have been looking at the what is that? The frequency response of the class of linear time invariant dynamic systems, and we saw that we wanted, sorry, yeah, we were looking at the frequency response of linear time invariant Poisson systems, and we saw that the Bode plot, right, was a very commonly used visualization of the sinusoidal transfer function. Similarly, the Nyquist plot is also a visualization, right, of the frequency response characteristics. So what is this Nyquist plot? So suppose if we are given a sinusoidal transfer function P of j omega, the Nyquist plot essentially plots the real part of P of j omega and the imaginary part of P of j omega in a complex plane as omega is varied. All right. So that is the Nyquist plot. Okay. So consequently, if we want to have a graphical visualization of this, right? It's just an alternative visualization, right? So we already looked at the Bode plot, which visualize the sinusoidal transfer function using its magnitude and phase, and we sort of visualize how the magnitude and phase varied with respect to omega. The main difference is that, if you have a complex variable, we can have a magnitude phase representation. We can also have a real imaginary part visualization, right? So suppose if we take the second order factor, omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared, right? So its Nyquist plot will be something like this. Okay, so this will be for the factor, omega n squared plus 2 zeta omega n s plus omega n squared, right? So I'm not going to go into the details of the Nyquist plot because we will be using Bode plot in this particular course. But I thought I should let you know what this Nyquist plot is, right? So that we are aware, as to what is this Nyquist plot. Okay, so that's a very brief introduction to Nyquist plot. Okay, so we will be using the Bode plot a lot, right, in our particular course. Okay, so once again, the Nyquist plot is just the plot of the real part of the variable P of j omega versus its imaginary part as we vary omega, right? Because P of j omega, which is a sinusoidal transfer function, is anyway a complex value function, right? It's going to have a real part and an imaginary part. Okay, so that's what we are plotting, right, using the Nyquist. All right. Okay. So now let me discuss the topic that we are going to look at very carefully today. We will look at what is called as the relative stability. Okay, so what is this? First, we'll understand what this relative stability is, why it is important, and then how do we evaluate the so-called relative stability of the class of systems under. Okay, so these are the various aspects that we will be looking at. So before we go into this discussion, let's recap the standard block diagram that we consider. So we have G of S as the forward path transfer function, and H of S as the feedback path transfer function. So we have negative feedback, and we have the reference input. We have W of S, and this is our E of S, right? So this is a standard negative feedback closed loop system visualization. So we can immediately recall that the closed loop transfer function Y of S divided by R of S is going to be equal to G of S divided by 1 plus G of S H of S, right? So this is the closed loop transfer function, and we also know that 1 plus G of S H of S equal to 0 is the closed loop characteristic equation, right? So and the solution of this equation are the closed loop poles, right? So this is something which all of us are aware of. Now, let's consider a graph, right? So I'm just plotting the S-plane on which I'm going to plot the poles of two, let's say, underdamped second order systems, right, in a relative manner, and then let's reason out, like what happens to them, right? So let's say we have system one, whose poles are like this, right? So they are very close to the imaginary axis, right? And let's say we have system two, whose poles are here, right? So this the green one is, let's say, system two, and the red one indicates the poles of system one. All right. So as we are already aware, if our poles are closer to the imaginary axis, the damping ratio is going to be small, and the race time is going to be very small, right? So the system is going to be much faster, right? And if we move away from the imaginary axis, the response is going to become a little bit more slower. With that understanding, if we look at this, example, like we can immediately observe something, right? So before we go there, please note that both systems are stable, right? Because both systems poles are in the left of plane, okay? So both S1 and S2, system 1 and system 2 are stable, right, to begin with, because their poles are in the left of plane, right? So there is no doubt about that, right? So now the question is, which is more stable? Okay, so essentially, which is more stable, and what will happen to these systems? When they are subjected to some uncertainty, right? So the question that we are going to ask ourselves is that how stable is the closed loop system when subjected to uncertainty? When subjected to disturbances / uncertainty. Okay, so that's an important question, right? Is it not? Because see, what do I mean by this? Let's say we take an example, right? So let's say we take the mass spring damper system as an example, right? So the equation of motion of the mass spring damper system is mx double dot plus cx dot plus kx equals f of t. Let's imagine that, like system one and system two are two mass spring damper systems, right? And system one is much faster than system two because its poles are going to be closer to the imaginary axis, right? So than system. Now the point is the following, right? So in real life, we are going to have variations in the system parameter, right? So this let's say the spring constant, right, k naught, right? It starts from a nominal value k naught. It's going to vary, right? It's going to be perturbed in real life around k naught, right? So we can have k naught plus or minus delta k. Similarly, this parameter c naught can also be perturbed in real life, right? So because as the system keeps on operating, the damping coefficient and the spring constant may change, right? So, and this is going to affect the closed loop system behavior, right? Is it not? So, if this is my original system to begin with, I designed some controller, but due to whatever reason, right, the open loop, the plant parameters change with time, and then what may happen, like we may end up in a scenario where the perturbations may be significant enough, right, to cause the closed loop poles to migrate to the right half plane. Okay, so let us say if we have these perturbations to be significant enough, right, such that the poles of S1 lie in this envelope surrounding the nominal pole. So let's say these indicate the location of the nominal location. Okay, but however, we can see that there is going to be a region around the nominal location in which we may say, hey, look, the pole is going to be, right? Now we can immediately observe that system 2 is more stable than system 1, right? Is it not? Because system 1 is faster, but that comes at an expense, right? Because what is happening? To begin with, both system 1 and system 2 are stable, right? The closed loop systems are stable, no doubt about that. All right. So now the question is, when the systems are perturbed, right, or there is some parametric variation, some changes which are what to say, naturally happening when an actual physical system in real life operates, right? So the question is, can these poles migrate, and if they are migrating, can they migrate to such an extent that they cross over to the right of plane, right? So then we can immediately observe that system 2 is going to be relatively more stable than system 1. Okay, that is where we, in this context, we introduce an adjective, absolute or absolutely. All right. So till now we are just looking at stability, right? So in this discussion, now we can see that we are going to introduce two adjectives, right? Absolute stability and relative stability, right? So we can note that S1 and S2 are both absolutely stable. So what do we mean by absolutely stable? We see that to begin with, their nominal systems are stable. Okay, no doubt about that. Okay, that is, the poles of S1 and S2 lie in the left of complex. However, we can say that S2 is relatively more stable than S1. I hope all of us can understand what is this notion of relative stability, right? So the bottom line is that, like, if you want our system to be relatively more stable, that is, like, it should have more robustness in the face of, let's say, like parametric uncertainties and system uncertainties. It should be, the poles should be further and further away to the left, right, from the imaginary axis, right? So that's an important requirement. However, like, it comes at a price, right? So if we keep on shifting the poles to the left, what is going to happen? The response characteristics get affected. So there is a trade-off, right? So on the one hand, we want the systems to be relatively more stable. That is, like, push the closed loop poles away from the imaginary axis. But however, there is a issue also, right? So that is, if we have the poles of the closed loop system further away from the imaginary axis, the closed loop system will become slower in transient response, right? Its response time will increase. So there is a trade-off, right, between the transient characteristics and the relative stability. Okay, so that's something which we should keep in mind. All right. So I hope the notion of relative stability is clear. Now the question arises is the following. All right. How do we evaluate this relative stability? Like, see, all of us now understand what is absolute stability, what is relative stability, right? So, yeah, absolute stability, once again, means that all the poles of the system are in the left of complex. Okay, no doubt about that, right? Relative stability means, like, what happens is that, like, we have, like, we are having, like, the closed loop poles to be further away in the left of complex plane, such that, like, even in the event of some parametric uncertainties, we are having enough robustness, right? The system doesn't become unstable. All right. So now the question becomes, how do we evaluate, right? Please note that if, let's say, we have the system S1, due to some parametric uncertainty, if the pole gets displaced from its nominal location, if it has to go to the right of plane, please note that at some point it has to cross the imaginary axis, right? So if it crosses the imaginary axis, what happens from this equation? 1 plus g of s h of s, right? That's what we are going to, okay? So if the closed loop pole initially in the left of complex plane, okay, were to cross over to the RHP, right? They should pass through the imaginary axis, right? They should first pass through the imaginary, through the j omega x. That's the imaginary, right? Now, in such a scenario, what can we say? We can say that whenever the closed loop pole passes the imaginary axis, we can say 1 plus g of j omega h of j omega equal to 0. How did I write this? We wrote it from here because 1 plus g of h of s equals 0 is the closed loop characteristic equation. Right? Now, if the closed loop pole were to cross the imaginary axis, what will happen is the following, right? So it will essentially make the closed loop pole as purely imaginary roots, right? So the closed loop pole now will be of the form s equals j omega, right? At the point of crossover. So if I substitute s equals j omega in that equation 1 plus g of s h of s equals 0, I get 1 plus g of j omega h of j omega equal to 0, right? So g of j omega h of j omega becoming equal to minus 1 becomes a very important equation, right? So I'm just rearranging the equation to get this, right? So the equation g of j omega h of j omega equal to minus 1 now becomes very important, right? I'm sure all of us can appreciate that, right? So this is something which becomes very critical in our analysis of relative stability. So what are we saying? Now, if the closed loop poles were to migrate into the right of complex plane, it will do so by cutting the imaginary axis at some point, and at that point, the sinusoidal open loop transfer function will become minus 1. All right. So this point minus 1 becomes very, very important. And as we know, if you look at the complex plane, the point minus 1 will have a magnitude of 1 and a phase of plus or minus 180 degrees. Right? So I'm sure all of us understand that. Okay? So we know that minus 1 is going to have a magnitude of 1 and a phase of plus or minus 180 degrees. So in a certain sense, what we are going to do is that we are going to use this equation to sort of like define parameters that will quantify how close are the closed loop poles to the imaginary axis, because the closeness of the closed loop poles to the imaginary axis defines relative stability, or what to say, essentially indicate the closeness is indicator of relative stability. Is it not? So then, given this, the question becomes, how do we use this equation to come up with a few definitions that will help us in quantifying relative stability. So what are these definitions? Let me write it down. We are going to define what is called as gain crossover frequency. So what is this gain crossover frequency, which we are going to denote by omega g, right? Gain crossover frequency, it is that frequency at which the magnitude of the open loop sinusoidal transfer function becomes 1. Okay, so g of j omega h of j omega is what we are calling as the open loop sinusoidal transfer function. So gain crossover frequency is the frequency at which the magnitude of this g of j omega h of j omega becomes equal to 1. Right? That's the gain crossover. Now, what is the next definition? The next definition is what is called the phase crossover. What is this phase crossover frequency? phase crossover frequency, which we are denoting by omega p, is going to be that frequency at which g of j omega p, h of j omega p, the phase is going to be minus 180. Okay, so it is the frequency at which the phase of the open important, because as we know now from the previous equation, right, that we just discussed. Okay, so g of j omega, h of j omega equal to minus 1 becomes very important, right, because that's the point at which the closed loop poles potentially cross over into the right of plane, right, by cutting the imaginary axis. So we want to evaluate how close are the closed loop poles to the imaginary axis, right? So that's what we are slowly defining. All right. So the gain crossover frequency is the frequency at which the magnitude of the open loop sinusoidal transfer function becomes equal to 1. Okay, and the phase crossover frequency is the frequency at which the phase of the open loop sinusoidal transfer function becomes equal to minus 180. Okay, so these are the two definitions. Now, based on this, we are going to quantify this relative stability first using what is called as gain margin. So, what is this notion of gain margin? So, let me explain what this is. Then we will let me first write down the formula, the equation. So, this is nothing but K subscript G is defined as the reciprocal of the magnitude of the open loop sinusoidal transfer function at the phase crossover frequency. Okay, so this is the definition of gain. So, what is this definition? Let me explain. Okay, see, at the phase crossover frequency, we know that the phase of the sinusoidal transfer function is going to be minus 180, right? Is it not? Now, if I find out the reciprocal of the magnitude of the sinusoidal transfer function at the phase crossover frequency, and I multiply the open loop transfer function by that number, the gain will, the magnitude of the new open loop transfer function will become 1, right? Because the reciprocals will cancel off, right? And so that sort of indicates, how close my close loop poles are to the imaginary axis, right? So please note once again at the phase crossover frequency, the phase of the sinusoidal open loop transfer function is minus 180 degrees, right? Is it not? Now, if I multiply the open loop transfer function by this number, the gain margin, the new gain, the new magnitude will become 1, right? And if the magnitude of the open loop transfer function becomes 1 and its phase is minus 180 degrees, then I skip this condition, right? G of j omega, h of j omega equals minus 1, and consequently, I will be crossing over, right? So that's crossing over into the right of plane, right? So that's why this gain margin is an indicator of relative stability. So this is equivalent to if you want to write it in decibel measure, so we take the logarithm and multiply by 20. So essentially, we will get it like this. Okay, so this will be in decibel measure. Okay, this is gain margin. So similarly, we have what is called a phase margin. Okay, so we can define a similar measure as far as the phase is concerned, right? So what is phase margin gamma? So now at the gain crossover frequency, the gain is 1, right? Now if I add some phase, negative phase at that point, then like what will happen is that like I will reach the minus 1 point, right? I can make the phase as minus 180. So that is what we want to look at. So gamma is defined as the phase of the open loop transfer function at the gain crossover frequency, which will be negative, and then we subtract it from minus 180 degrees, so that we find how far it is away, right? So the formula for gamma will be 180 degrees plus the phase of the sinusoidal transfer function and the gain crossover frequency. So now if we add this much amount of phase lag, right, or negative phase, right, what we get as phase margin to the open loop transaction. So what will happen is that like we will have the open loop transfer function passing through -1, right? Because of the as at omega g anyway the magnitude of the open loop transfer function is 1, right? So that's the definition of omega g, right? Is it not? So if we have that, like, and if we add this corresponding phase lag, like, I'm going to pass through -1, right? So that's something which is undesirable, all right? So that's the notion of phase margin. Okay. So gain margin and phase margin put together quantify relative stability. So we want gain margin to be greater than 1 and phase margin also to be positive for the closed loop system to be relatively very stable, right? So that's something which we want to have, all right, in the first. Okay. So let me illustrate these with an example. Okay. Before I go into the example, are there any questions about these, about the concept of relative stability and these definitions?
The phase margin, can you explain a little bit, sir?
So what is the phase margin? So suppose, see, we know that at the gain crossover frequency, right, the magnitude of the open loop transfer function is anyway 1, right? Now, how can I make the system to be unstable? I need the magnitude to be 1 and the phase to be -180, right? So now the question becomes, can I calculate what will be the difference between the actual phase at the gain crossover frequency and then -180, because -180 becomes very critical, right? As far as the phase is concerned, right? To go to instability. So if I'm able to calculate this difference and essentially make the system slower by this phase, I'm going to pass through the -1 point, right? Because at the gain crossover frequency, the magnitude is 1, right? So that is how we are evaluating in a certain sense how we are going to go to -1, all right? So in a certain sense, see, what are we trying to do? We are trying to see how we can quantify relative stability by looking at how we can make this open loop transfer function go to -1. See, there are two ways in which we can make the open loop transfer function go to -1, right? We keep the gain the same and then like we push the phase to a higher negative value so that we reach -180. That is what is quantified by phase margin, right? The other way is that we keep the phase at -180 and then we scale the magnitude such that we make the magnitude to be -1. So that is quantified by the gain margin. So these are notional quantities that quantify two ways in which I can go to the -1 point, right? And that's what we are using to sort of like quantify the notion of relative stability. Is that clear?
Yes. Yeah.
Okay. So we'll do an example that will make things even more clear. So let us consider a unity negative feedback system, right? Sorry, not a unity negative feedback closed loop system. So, but once again, you can see the importance of the open loop transfer function, right? So just like before, this definition of open loop transfer function becomes very, very important, right? Okay, with the open loop transfer function g of s h of s being equal to, let's say, some 1 by s times s. Okay, so what we want to do is that like calculate the gain margin and phase. Okay, so we want to calculate these two. All right. So now, what do? We essentially calculate all these parameters. Of course, first to begin with, we can immediately observe that if we look at the closed loop characteristic equation, right? So 1 plus g of s h of s equal to 0. We will immediately see that this will become 1 divided by 1 plus s squared plus s equal 0. So the closed loop characteristic equation will be s squared plus s plus 1 equal to 0, right? So do you think the closed loop system is absolutely stable?
Yes, sir.
Yes. Why? Because this is a second order polynomial with all the
Signs are
coefficients being being of the same sign, right, and non-zero, right? Correct. So by Routh's criteria, you can immediately conclude that this closed loop system is absolutely stable, right? Closed loop poles are in the left of plane. So closed loop system is absolutely stable to begin with, right? Because we should ensure this, right? Is it not? See, we can talk about relative stability only if the closed loop system to begin with is absolutely stable. We are just checking that. All right. So let's right? So now we anyway go and look at the sinusoidal transfer, open loop transfer, right? G of omega, G of j omega, H of j omega. That's going to become 1 divided by j omega times j omega plus 1, right? So you substitute S equals j. Now we can immediately see that the magnitude of this is going to be magnitude of g of j omega, h of j omega. As we already know, if you have products and ratios of complex variables, the magnitude is going to be the same ratio of the individual magnitude, right? The magnitude of j omega is just omega. The magnitude of j omega plus 1 is omega squared plus 1, right? So square root of real part squared plus imaginary part squared, right? So that's what. And what about the phase of g of j omega, h of j omega? See, look at the phase of g of j omega, h of j omega. The phase of 1 by j omega is minus 90, right? We already know that, right? Because that's the integral term, right? 1 by s, right? And the phase of 1 by j omega plus 1 is going to be minus tan inverse of omega, right? So this is something which we already know, correct? So I'm sure by now all of us are familiar with how to write this, okay? Because there are two terms, right, in the open loop transfer function, 1 by j omega and 1 by j omega plus 1, right? The phase of 1 by j omega is going to be 90. The phase of 1 by j omega plus 1 is going to be minus tan inverse omega, right? So those are the two phase contributions, right? So these are the magnitude and phase. Now what do? Let's first calculate the gain crossover frequency. If we calculate the gain crossover frequency, we need to calculate the magnitude, at what frequency the magnitude of g of j omega, h of j omega becomes equal to 1. So if we look at this, we need to calculate what will be the frequency at which 1 by omega g times square root of omega g squared plus 1 will be equal to 1. Okay, so that's what we have. So this can be solved in a very simple way, right? So at first it may look like it's complicated, but it's not. We cross multiply, we get omega g times square root of omega g squared to be equal to 1. Now we square both sides. What do we get? We get omega g squared times omega g squared plus 1 is equal to 1, right? So that's what we have. So if we expand it, what are we going to get? We are going to get omega g power 4 plus omega g squared, and then we bring the 1 on the RHS to the LHS. So once we bring it to the left hand side, we get omega g power 4 plus omega g squared minus omega 1 equal to 0, right? Now this is a fourth order polynomial in omega g, right? And we need to solve for omega g, right? How can we do that? Any idea?
By factorization.
By factorization. Any other thought process? No.
Or splitting into two second order polynomial.
So in fact, what you can do is that, like, you can essentially see that this particular what to say, polynomial, although a fourth order polynomial, is a polynomial only with even powers of omega g and the constant term. So one could say that this is a quadratic polynomial in omega g squared, right? If you say you substitute omega g squared to be some omega 1, right, you will get a quadratic equation. So we can immediately solve for omega g squared, okay, as minus 1 plus or minus square root of 1 then plus 4, right? B squared minus 4ac by 2a. 2a will be 2, right? I hope it's clear how we got this. right? So we are essentially solving for omega g squared, right? So I hope that is clear. So if we solve this, please do this as an exercise. Double check my solution. We are going to get plus 0.618 and minus 1.618. Okay, so that's what we are going to. All right. So immediately we can see that this will be eliminated. Why? Because omega g is going to be a real number, right? Positive number. So now if I take square root, I can take square root of minus 1.618, right? So that's going to result in an imaginary value. So we just take omega g to be the square root of 0.618, and that will give us 0.786 radians. Okay, I hope it is clear how we got gain crossover. All right. Okay. So now, if we look at the phase crossover frequency, any questions on how we got omega g? No.
No, bro.
Yeah. All right. So now, if you look at the phase crossover frequency, we want to see at what frequency the phase of this open loop transfer function, sinusoidal open loop transfer function, becomes 180 degrees, right? So this implies that in our case, minus 90 degrees minus tan inverse of omega p will be equal to minus 180, right? Or we are asking ourselves the question, what is the frequency at which tan inverse of omega p becomes minus 90, right? So this is the question we are asking ourselves, correct? So what do you think will be the frequency at which tan inverse of omega p will become minus 90? Right? Because tan inverse of infinity is going to be minus 90, right? So the angle will tend to minus 90 when the argument of tan inverse goes to uh, infinity, right? So that's what we will have. So consequently, the phase crossover frequency is going to be infinity, right? So it's going to tend to infinity, right? So I hope that is clear. All right. Now we calculate the gain margin and the phase margin. So the gain margin is going to be equal to, if you recall the definition of the gain margin, is the reciprocal of the open loop sinusoidal transfer function at the
Sir,
phase
I think
crossover.
it should be plus 90 degree.
I'm sorry, what is it?
I think that should be plus 90 degree.
1 minute, 1 minute. Let me will be minus tan inverse minus 180. Yeah, okay, sorry. Okay. Yeah. All right. Yeah. Thank you.
Yes.
Yeah. So you can see that tan inverse. Sorry, I missed a minus sign. Thank you. Yeah. So essentially, but omega p will tend to infinity, right? So I hope everyone agrees with that, right? So now we can immediately observe that the gain margin is going to be the reciprocal of this magnitude at the phase crossover frequency. So we are looking at the reciprocal of the magnitude is omega times omega squared plus 1, right? Evaluated at omega equal to infinity. So what can we say about the gain margin? It is going to be infinity, right? Because when we substitute this, right? Sorry, this is going to be 1 by, I'm sorry, I think I missed reciprocal. This is the magnitude. I'm sorry about that. 1 minute. Let me be very careful. So this is going to be reciprocal of this, right? So the term in the red bracket will go to 0, right? As omega tends to infinity. I'm sure all of us can look at it. Now we are going to have reciprocal of that, right? So that will go to infinity, right? So I hope everyone can agree with that. All right. So we have infinite gain margin, which is very good, right? So we want gain margin to be a positive value and as high a value as possible. So that means that whatever we do, if we scale the magnitude of the open loop transfer function, we can never make the system unstable. Okay. So that is the what to say physical meaning of this particular result. Okay, the gain margin being infinity means that if we multiply this open loop transfer function by whatever magnitude, right, the system is not going to become unstable. All right, so that is the positive result from it. That's how we should interpret. Now, what is the phase margin gamma? Phase margin, as we wrote down, is going to be the magnitude of the sinusoidal transfer function, the open loop sinusoidal transfer function, d of j omega, h of j omega, omega g plus 180 degrees. So what will we have? We will have the phase of the open loop transfer function is going to be minus 90 minus tan inverse omega g, right? So we already saw it here, right? So that's the expression for the phase, right, of the open loop sinusoidal transfer function. So I'm only using it with omega equals omega g, then plus 180, right? So now omega g, this term will become tan inverse of 0.78, right? So if we simplify and evaluate this, we will get this as 51.8. Okay, so please check this answer. Okay, so this will be the phase margin gamma. Okay, so this is also good, right? So because now we have a positive phase margin, so what it means is that if we add a phase lag, okay, suppose let us say we have a system, we have this system, and we essentially add a lag, okay, of 52 degrees, okay. Only then, like we are going to essentially have the system becoming unstable. Okay, so that is something which is very, very good, right? Is it not? Okay, so that is the notion of phase margin. Okay, so what does this phase margin indicate? The phase margin indicates that, like if we have this system and we retain the same magnitude, however, we are essentially adding a phase lag, okay, of 52 degrees, the system will become unstable. Okay, the closed loop system will become unstable. So, but till if a phase lag of 52 degrees is added, this is closed loop system is going to be stable. All right. So you can see that we get quantitative measures, right, of relative stability, right, through this example. So to summarize, as far as this particular example is concerned, this gain margin is infinity is very good because what it tells us is that, like, doesn't matter what number I multiply the open loop transfer function with, I will never make the open loop system, closed loop system unstable, right? That's point, right? So the phase margin is telling us that, like, okay, we add some phase lag to the system without changing the magnitude, right? But however, like we are not going to, we will be fine, right? As far as until, like we don't exceed the phase lag of 52 degrees, right? So that's what it is telling us. Okay, so that's how gain margin and phase margin are important quantifiers, right, of relative stability. All right. Okay. So any questions on this?
No, sir.
Okay. So the last concept I want to essentially convey to you as far as the frequency response and this analysis is concerned is the following. So let's say we consider the closed loop transfer function, right? Y of s by R of s, which is g of s divided by 1 plus g of s h of s. Suppose, let us say we plot the magnitude of the closed loop sinusoidal transfer function. So what do I mean by closed loop sinusoidal transfer function? We plot this is omega, the magnitude of y of j omega divided by r of j omega. That is, we substitute s equals j omega in this equation, right? Okay. We substitute s equals j omega, the closed loop sinusoidal closed loop transfer function to get the closed loop sinusoidal transfer. Let us say, I'm just taking example. Let us say that magnitude goes like this, right? So now, if we draw a line, a horizontal line, which is 3 decibels lower than the low frequency magnitude, okay, of this closed loop transfer function. This is 3 decibels lower, okay. So 3 decibels lower, okay. Now we look at the first frequency at which it cuts the magnitude curve, the log magnitude curve, all right. So that frequency is what is called as a cutoff frequency. Okay, omega c is what is called as a cutoff frequency, and that is defined as the frequency at which the magnitude of the closed loop sinusoidal transfer function is lower than its zero frequency asymptotic value by 3 decibels. Okay, so the significance of -3 or lower than 3 decibels is that when you have a difference of a direction of 3 decibels, we are reducing the magnitude by 1 by root 2 in absolute terms. Okay, so that is the equivalence, okay, in terms of absolute magnitude. And so omega c is what is called as a cutoff frequency, and the region 0 to omega c is what is called as a bandwidth of the system. Okay? These are important parameters which quantify performance when we want to design controllers using frequency response. Okay? So these are all, these become important, right? So, and there is another parameter which is called as cutoff rate. I'm sure we would have heard the what is the term bandwidth in many places, you know, particularly when we deal with sensors and so on. This is what is the formal definition of bandwidth. So what it indicates is that like we want bandwidth indicates how good a system's response is, right? So because if omega c is very high, then the bandwidth is high. That means that the system is going to allow sinusoidal signals of a very high range of frequencies to be passing through it, right? And it's going to essentially tolerate sinusoidal signals of a very high frequency band, right? So that is something which is positive, right? So we may want high bandwidth systems, right, in real life. But then there is a price to pay, right? So what is the price? The counter, what to say, measure is that like such systems with high bandwidth become expensive and complex. So there is a trade-off, okay, between bandwidth and cost complexity. Okay. So there is another parameter called cutoff rate. What is this cutoff rate? Sorry. Again, cutoff rate is nothing but the slope of the log magnitude plot at omega equals omega c. Okay, at the cutoff frequency, we find out what is the slope, okay, of that curve. Okay, so higher the cutoff frequency, we see that cutoff rate. We can conclude that the high frequency signals will be attenuated at a faster rate, okay, which may be preferable. All right. So these are some parameters which we need to remember, and when we do essentially the controller design, right, using frequency response method. See, when we did controller design previously, we looked at settling time, rise time, peak overshoot, and so on, right? Peak time and so on, right? So although that those measures were derived using transfer functions, which are complex valued functions, we typically say that that has to do with, you know, like a time response based design method. So what do you mean by time response based design method? If you recall, we got the definitions of rise time, peak time, time constant, settling time, overshoot, and all by looking at the response of first order and under and second order systems to step input, all right, which was like a transient input, right? It was with norm. Now, that's why they were called the corresponding methods using root locus and Rouse criteria. Typically, people call them as time response based. Now, when we use frequency response, yes, we are still going to analyze transfer functions in the complex domain, right? But since we use sinusoidal inputs, right, which follow sort of the same pattern, which are periodic signals, right? So we call them as we call this class of methods as frequency response based methods, and the corresponding specifications, okay, which are used to quantify the performance or expectation of the closed loop system are gain margin, phase margin, okay, what the parameters that we have learned today, bandwidth, okay, cutoff rate, and we would have looked at the resonance frequency, right? We looked at resonance frequency omega r times omega n times square root of 1 minus 2 zeta square, right? That's one. And the resonant peak. Resonant peak is nothing but the magnitude of the open loop transfer function at omega equals omega r. Okay, so that is the resonant peak. Okay, so what is m subscript r? M subscript r is nothing but the magnitude of the open loop transfer function at omega equals omega r. Okay, so that is what is called as resonant peak. Okay, so these are some parameters, right, which are used to quantify performance when we design controllers based on frequency response. All right. Okay. So that concludes our discussion of frequency response and a classical control in totality. So from the next class onwards, we will go into state space representation and design of controllers using the state space method, okay, which fall under the realm of what is called as modern control. Okay? So we will get started with modern control theory in the next. All right. Okay. So are there any questions based on what we learned today?
Why we select 3 dB sir below?
3 dB. So if you look at it, if you look at a difference of minus 3 dB, you will see that this will go to an absolute reduction of 1 by root 2. You can check it yourself. Okay. So in fact, if you take the Laplace, sorry, not the Laplace, anti-log. Okay. So 1 minute, let me pull the calculator. Okay. So if you look at a reduction of 3 dB. Okay. So what I'm going to do is that, let's say we take a reduction of 3 dB. Okay. Sorry. 3 is equal to minus 3. Okay. We do 10 power x. Sorry. We divide by 20 first. Okay. Let me repeat it once again. Minus 3 divided by 20. Okay. It will be this. Then we do 10 power x. You see that this is going to be 0.707. Okay. So that's going to be 1 by root 2. And if you take the power sort of like the power amplitude, right, or the square of the amplitude, you will get 0.5. Okay, so people say that the power or the energy of the signal, right, is half. Okay, at a magnitude of 3 decibels difference. Okay, so that is the convention. Okay. Okay. Yeah. It's a convention. It's a definition.
Okay. Okay.
So a reduction of 3 decibels means in absolute magnitude we reduce by 0.707, right? And if you square it to get sort of what people will call as an equivalent energy or power measure, you see that the energy or the power measure is halved, right? When you decrease the magnitude by 3 decibels, right? So that's why we take 3 decibels. It's a convention. Okay. Any other questions? All right. So if not, let me end today's class here. Thank you.